All right, sorry about that. I hope that I'm audible now. Yeah, so once again, hi guys, I'm Athar. Welcome to the Automation in Robotics intro session. I hope you enjoyed the mechanical intro session that just happened. Today, I'll just be giving a broad overview of the automation field so that you can get an idea of what's there to explore in the field and also some resources and how you can get started. So let's dive in. Well, in the next half hour, I'll be covering various advances in robotics. How does automation fit into robotics? How can you get started? Some resources for you, and we'll have a Q&A session at the end. So please ask any questions on the Discord channel or in the chat. So I'll be answering those at the end. Yeah, so just a note on the recent advancements in robotics. So recently, in the last 1 or 2 decades, robots have become smaller, more capable, and more reliable. So by smaller, some examples are maybe you have a Roomba or an autonomous vacuum cleaner at home, those small robots that run around and clean your floor. So by more capable, you can have drones which, say, a decade ago had to be manually controlled, but now have automation capabilities. So they can follow you around and they can pretty much act on their own. And they're available in the mass market now and also more reliable. So on the right, you can see this industrial hand robot, which is capable of machining precision instruments. It's capable of making precision things, picking up and placing things, and working in factories to make various sorts of items and in an industrial scale. Other examples of robots creeping into day-to-day life are there when you say order something on Amazon. The order gets sent to a warehouse where there's an army of warehouse robots which pick up your item and place it uh, into the correct shelf, which gets placed into the correct say truck. And then we don't have autonomous trucks yet, but soon enough, if we believe Amazon, we might get autonomous drones for delivering them. So robotics has come a long way in the last 2 decades. And the reason for most of these developments has been a huge increase in the efficiency of hardware, much better and cheaper actuators. So I think Dixit must have told you about actuators. So these are things like motors and anything that can create motion in a robot. Also, a lot of useful software tools which have been developed in the last decade, which have made making robots and researching much easier. We also have a lot more efficient algorithms, which can do things with a lot less compute and can do them on smaller robots so that you don't need large computers every time you want to do something smart. So let's talk about how automation fits into all of this. The components of a robotic system, by now you might have an idea. We have mechanical design, electronics, and automation. So mechanical design, you might have seen, was designing and basically determining the physical constraints of a robot and then designing a physical body so that it satisfies those constraints. Electronics is the brains of everything, where you have this processing power which processes the commands that are generated into suitable signals. And today we'll be talking about automation, which is the third major part, which decides what those commands will be, makes the actual decisions in how the robot is going to move, where it's going to move, and all of those things. So we'll be talking about automation today, and we'll have a session on electronics soon enough. So if you're interested in electronics, don't worry, we have you covered. Stay tuned on our Discord, and we will be announcing the details of that soon. So, automation. We can divide automation into three different things again. The first is perception, and then is planning and control. So, this is very similar to how humans behave. Humans take in the surroundings around them. So, we usually hear things that are there around us, we can see things that are there, and using these two senses, we build a map of our surroundings. It's not a pen and paper map, but just generally in our heads, we have a sense of where everything is. So in this video, if this works out, let's see. Hopefully this is visible. So on the bottom left, you can see that what the camera is seeing for the robot. And the robot is converting this camera image into a depth map. So a 3D map of its surroundings, which it's storing in its memory. And this is all happening real time, where the robot is actually seeing all of these things, and it's get to see the. Okay, sorry about that. Yeah, it got to see everything, and it made this 3D map of its surroundings. Now, once you have the map, you can decide what you're going to do in this environment. So usually robots are given a goal to do. So you have to navigate to a certain place, or you have to pick up a certain item. So the robot has to plan how it's going to do them. What are the various waypoints that it has to reach? What are the various signals that it has to send out to achieve its task? And that's encapsulated in planning. And we can see an example of that here, where we have a car which is told to navigate a maze, which it doesn't know about yet, but it has a goal point, and you can see that it's computed a path, it's planned this path, and it's dynamically changing its path according to what it sees around it. So as it sees more and more of the maze, it adjusts its path. So it realized, okay, I've gotten into a dead end, let's try out a different path. And here we can see the orange lines that you can see around the car, if we look at that again, are actually the trajectories that the car has tried out. So the car is in its mental map that is created. The red lines that you can see are the mental map. And then the orange lines are the various guesses it has made of where it can go. So it has guessed that, okay, it can go down back where it came from, or it can try out this way. And of those guesses, one of them has turned out to lead to a path to the goal, and it started to follow that path. So this creation of this path and planning of that path is, yeah, encapsulated in planning. And it's not just path planning, right? It's deciding what decisions you're going to make when faced with different scenarios. So that's talking about more intelligent robots. Or you can also have motion planning. So when, say, a robotic arm has to move from one place to another, it there are multiple different ways you can move it. So if I want to move my arm from, let's see if you can see this, if I want to move my arm from here to here, there are multiple different joints that can work. Maybe I can move my shoulder joint up, maybe I can just move my elbow joint in such a way, or my wrist joint, and all of these things have to be coordinated in some way. So that is all encapsulated in planning. And after you've made the plan, you have to execute it, and that's where control comes in. So a really cool example of control is this control of a quadcopter, where the command we've given to the quadcopter is stay at a certain height, and no matter what happens. So there are various algorithms running on board that quadcopter called controllers, and these controllers are determining the electronic signals to send to the motors, which will keep the quadcopter at that certain height. So no matter if there are any sensor inaccuracies, or if there are any disturbances due to wind, or as we can see here, human interference, the robot will always try to get back to that position. So this is a very simple but really cool example of how control works. And you have these three things which make up the base of automation. These are three independent subsystems which work together and can create really cool behavior, and behavior which we can ultimately call intelligence in a robot. So, okay, what happens when we put all of this together? So I've prepared some cool examples here again. And you can see, if you missed that, the experimenter is throwing a ball and the quadcopter is dodging that ball in real time. So that means it perceived that the ball was there using the camera that it had, as you can see in the top right and top left. And then it planned that it had to, I'll just play that again. It planned that it had to move to the right a little bit and tilt a little bit just to avoid the ball that was coming in its path. So it planned that path, and then finally it executed it using control. So the controllers on board got the plan from the planner, and they gave out the electronic signals to the motors so that the quadcopter tilted to the exact degree that was required. We have another example of these three subsystems coming together in here, where we have a quadcopter which is exploring a cave autonomously. So again, it is perceiving the area around it as this depth map that you can see, and then it's planning a path where you can see all of these waypoints that have been planned, and then a controller on board is sending out the electronic signals again to control the path. So you can see it's a similar pattern of perceiving your surroundings, planning a path or planning some decisions to do in that surroundings, and then executing them using a controller. So some ERC projects that have been related to automation one has been Trotbot, which you might have seen. So Trotbot is supposed to be an autonomously navigating ground robot, which has on the top of it a lidar equipped. So lidar is short for light ranging and yeah, light ranging and detecting. So the lidar sends out light beams in all 360 directions. So it's a spinning laser basically, and the laser sends out pulses. And there's also a detector next to the laser which receives those pulses, and using the time difference, it can determine how far away a point is, the next closest point is in that direction. And then it can create a 360-degree map of the surroundings in that way. So that's how we're using perception. Then for planning, we are using a mini computer on board to plan using some algorithms that such as RRT and PRM and these different types of sampling based algorithms which can guess different paths in its surroundings, and then the best guesses are the ones that are followed. And then we have a Raspberry Pi on board which has a controller running which controls the omni wheels. So if you attended Dixit stock, you'll know what omni wheels are, in that they can move in any direction. It's not like a car which has to move forward, and if it wants to turn, the wheels have to rotate. Here we can move in any of the 360 degrees that we want. So we have a controller which moves the robot around wherever we want. So that's Trotbot. If we were on campus, we could have showed it to you physically, but unfortunately, all we have is the picture. You can find out more about all of these projects on our website, ercbpgc.github.io. And yeah, you can check out the code for these and also more pictures and stuff. So if you want to find out more, there's also a Python library for path planning that we've created called GenNav, which is supposed to be a modular path planning library where we can easily implement new path planning algorithms that might be invented. So path planning research is moving really fast, and we wanted to kind of create a library in which it's really easy to implement new algorithms and test them out and compare them with each other. So that's what GenMap does. And all of these other projects on the left, on the right, EchoSlam, Romanov, Carbaroum, Spiderbot, all of these require some degree of automation. So they all require some sort of perception, some sort of planning, and some sort of control to get them to be intelligent. So up till now I've talked about the classical side of automation. Now, in the recent decade, due to the rise of machine learning and especially the use of neural networks in machine learning, leading to this new field that we know as deep learning, there have been a lot of new advancements in automation, and a lot of new things have been tried. So before, to automate a robot, you would have had to write these algorithms, which guess different paths and then choose ones that are good. And you need to have these complex algorithms which create a map of the surroundings in which the path has to be planned. Now we have reinforcement learning, in which a robot can learn to navigate in its surroundings purely based on its experience. So the robot has been trained in simulation to behave in a certain way, and it hasn't been taught any specific algorithms as such. It's just been trained that if you want to go, you can go to a goal, and whenever it does get to a goal, it was told, yes, you were right. Whenever it doesn't go to a goal, it was told you were wrong. And this is done millions of different times in simulation. And when it's applied in real life, you can see the robot actually behaves intelligently. So it saw the dog, it waited. And here the human experimenter is annoying it, so it kind of turned around, and then it carried on back on its path. It goes down the corridor. And so here it's a really big leap, because we don't have to spend human time working on different kinds of algorithms, but we can rather devise techniques in which robots learn by themselves how to perform different tasks. And one example that was shown here is navigation. Another great use of machine learning is through computer vision. So uh, some of you might have heard about a special type of neural network called convolutional neural networks, which are very useful for detecting things in images. So that here we can see an application of an autonomous car which is navigating a street, and the red boxes that you saw were objects that it had detected in its view. and computer vision makes it really easy to detect these objects, whereas it was very hard to do them through classical means before deep learning came along. So these were just some new frontiers that we had so far. Yeah, and now the question on your mind must be, how do I get into it? I hope that I kind of gave you some excitement about this new field and got you a little bit hyped up. So, how can you get involved? Well, the skills that you need are programming and math, and that's it. It's a pretty short list. So if you know these two things, and obviously that you have a curious mind and you know how to use Google and you know how to read, with these things, you can pretty much attempt or try out or contribute to any of the things that you've seen so far. If you know programming and if you know your mathematics really well. So let's talk about this a bit more detail. What do you mean by programming, you ask? So in programming, up till now also, I've gotten a lot of questions in Discord and WhatsApp, and we've had some discussions also so far about what languages are good to learn for robotics. And many of you might not even know any programming languages so far, and that's completely fine. Some very useful ones that I recommend you start learning now are Python, C++, or C, and MATLAB and Simulink. So these are the ones that are most relevant to robotics. Python is used in basic robotic tasks such as for simulations or for for simple automation scripts or testing out or sandboxing different ideas that you might have. And Python is generally the first language most people learn because it's really easy to learn, and it's not just useful for robotics but also web development and machine learning and a broad range of things. So I would recommend starting with Python. Um, Another choice you have for a general purpose programming language which is really useful for robotics is C or C++. So they're basically C++ is just an extension of C, and if you can learn one, it's really easy to pick up the other. And C and C++ are generally used for embedded systems. So stuff like if you want to program your Arduino or any other STM32 or any other microcontroller, you'd be using you'd be using C or C++. And yeah, if you it's not just useful for embedded systems, but it's also useful for the kind of automation that you just saw. So implementing path planning algorithms or useful in machine implementation of machine learning algorithms. And the reason why, yeah, so for simple, you can segregate Python and C++ into two ways, in that Python is used for simpler things and C++ is used for harder things. And by harder, I mean stuff that is actually implemented in industry or stuff that you actually want, where you care about speed and you care about performance and energy consumption and all these things. So C++ is really useful if you want to write some efficient code. And MATLAB and Simulink are generally used where in experimentation and research, where maybe want to model a robot, or you want to so if you have a robot in mind that you want to build, before building it you can describe it in terms of mathematical equations so that you can simulate it. So by that I mean simulate the dynamics of how it would move around, depending on its weight and depending on what kind of motor torque that you would give, and the interrelation between all of these. And I think you will have an idea of how this works uh, from back in your 11th standard physics, right, where you can model throwing a ball as projectile motion using a set of equations. So MATLAB and Simulink allows you to model a robot as a set of equations and then simulate it. So again, this might be a lot of information, but if you're really new to programming, if you don't have any idea of what to do, I would suggest start with Python. And once you know a language, it's really easy to pick up any other language. Yeah, because they basically follow the same kind of principles. So the second important thing is after you know a programming language, programming isn't just as simple as writing some code into a text editor and pressing run. There's a lot of different steps that are involved in between. The first is your operating system. So we've also had a lot of questions about which operating system do I use if I want to code. And generally people have Windows to begin with, but most of the robotics tools that are used and platforms that are used are mostly supported for Linux and don't really have as much support on OS, on Apple OS X or on Windows. So it's really good to either dual boot your laptop with Linux, and if you can't dual boot for some reason, Windows has an inbuilt Linux simulation kind of thing called Windows Subsystem for Linux, so you can check that out. Or you can always run a virtual machine. So it's always good to get used to Linux as a development environment and start coding in that because it supports coding in a much better fashion than Windows. Also, I highly recommend getting comfortable with the command line. Generally, most of our life we use the mouse to click stuff and drag and drop stuff, and the mouse and the keyboard is used a little just to type in the text that we need. And this is fine for everyday use. But if you want to start coding, and this is not just for robotics, it's for anything from web development, machine learning, or any other field that you want to code, any operating systems code, anything basically. You need to have some comfortable, like you need to be comfortable with using the command line. You need to know what the commands are for doing certain things. You need to be able to navigate files and folders. And so if you were just given a command line and no graphical user interface, you should be able to get around and get the job done at least. And after a while, you start understanding that command line usage is just much faster for coding than using the graphical user environment. So I would recommend at least playing around with it a little bit to understand how it works and what the basic functionalities are. And finally, version control. So you might not need to get into this just yet, but it's always good to be familiar with what Git is. So suppose you're in a team and you're working on the same program. So your program might be made up of 3 or 4 files. Now, since you're working in a team, you might be editing the same files at the same time, and it might get really confusing really fast, right? Who made what change? What if someone overrode the change you just made and that broke the whole code? And how is there any way to redo it? And all of these things can happen. So Git was made for these exact scenarios, and it provides you a way to work on a group, work as a group on the same piece of code, and keep track of all the changes that have been made, and be able to roll back those changes, be able to work in a very organized manner. So this might seem trivial, but it does a lot of wonders when you actually start using it. And the best place to start using Git is make an account on GitHub. And GitHub is not just a website that runs Git, it's also a lot more. It's basically a social media network kind of thing for open source. And for those of you who don't really know uh, open source is basically a whole community of people who write code and let anyone see their code and let anyone propose changes to their code and discuss over that code. And most of the things, such as the operating system Linux or a lot of robotics platforms, are written in an open source manner and are available on GitHub or on similar platforms. So it's good to get familiar with GitHub and Git in general. Don't worry if you don't really know about this right now, but it's just good to know that it's out there and you might encounter it sometime in the future. And finally, this is specific to robotics, are open source platforms. So over the last 10 years, robotics has had a really cool and flourishing open source culture. It's really driven by this one organization called Open Robotics based out of California. And they started making all of these open source tools, such as the ones you see here, the robot operating system and Gazebo. I'm not sure if Move It was made by them, but they started making these really cool tools, and it made it easier for regular people like you and me to build and test our own robots. The Trotbot that we made runs the robot operating system, and it wouldn't be possible to, or it would be much harder for us to program the Trotbot without it. So it's really, these are some really cool platforms which allow us to do advanced things without much effort. And just a small intro about all of these. ROS, the robot operating system, isn't actually an operating system. But imagine if you wanted to develop a robot which helped around the house. So it would have to be able to pick and place things, maybe understand speech commands, and also navigate without bumping into things. Now, these three things you could write as a single program, or you could break them up into independent programs that communicated with each other. it's much easier to write them in independent programs, right? And what ROS does is a framework for you to write those things as independent programs and allow them to communicate with each other so that everything happens in a coordinated manner. This is a very abstract thing, but yeah, if you start actually using it, you'll understand how useful it is. Gazebo is basically a simulator for robotics, which lets you test robots on the computer and test code for robots on the computer instead of having to put it on a actual robot, which might not be accessible or which might be expensive to use. And Move It is a library for robotics, for automating robotic arms and those class of robots in general. And there are a lot more of examples that can give of open source platforms that have been really helpful in robotics. So this is just the general picture. For programming, you need to be familiar with different, at least one language, and I would recommend starting with Python. You need to know what a development environment is and be familiar with an operating system like Linux, and be comfortable with the command line, and also know what open source platforms that are out there. And coming to math, I'll just go over this quickly because you'll be learning all of this in college anyway. But the important thing is to pay attention to at least linear algebra and calculus. So linear algebra is really helpful for things such as frame transformations. So if you're in, say, if you're trying to automate a robotic hand, then the frame of your wrist would be different from the frame of your shoulder. So you need to be able to transform some command that you have from the shoulder to the wrist. And there are a lot more examples that maybe you can think of in along similar lines. It's also useful in machine learning, so stuff like linear regression and neural networks, which are purely based on linear algebra. And calculus is also important. So the control theory I talked about, the controllers that are used to keep things stable, to that allow the commands that we generate through the planner to be executed on a real robot in a stable manner. All of those controller algorithms are based on differential equation theory, and there's a lot of research being done into these. But to understand any of these, you need to understand basic calculus at least. And also, if you want to get into research around these and you want to read research papers or you want to implement some modern ones, then it's good to understand it's good to be comfortable with higher level calculus and also differential equations. So make sure you pay attention to these when you're doing them in class, and also maybe look up some of these things on your own. So at this point, you might be feeling a little overwhelmed. There's so much to learn, there's so much to do. When am I ever going to get to actually work on a project? And yeah, there seemed like a long way to go between here and actually getting things done, right? You maybe need to put in a lot of effort, and you might think you need a lot of time to get there. Well, my message for that is just to keep calm and carry on. We've all been in this situation where we've seen, okay, there's a lot to learn, and we don't really have much time, and okay, what am I going to do? And where am I going to start learning? Another problem that people might have is that I want to start learning Python, but where do I start? There's so many resources online. So all of these issues we've already had, and we kind of wanted to help you on that journey. And for that, we have created a collection of resources, uh, a sort of roadmap for a complete beginner to get started with these kinds of things. So this has resources from things for all things related to automation, electronics, and mechanical. So you can check this link out, and it has resources for. So I talked about programming languages, development environment, and also open source software. So it has resources on how you can learn more about them. Also, good places where you can learn Python, C++, and MATLAB. Also, places where you can learn control theory and where you can learn about path planning and all of these things in a beginner-friendly manner. So please head over there if you want to get started and if you want to know more about any resources you can have. And once you get there, the most important message I have for you is take things one at a time. Yeah, again, this doesn't really solve the question of there are so many things, but what do I do? If you start, like what I've personally seen from my personal experience, is that if you start learning things one at a time, you generally it becomes easier to learn more things in the related field. So Simple example is programming languages. If you learn a programming language, it's much easier to learn the next one. If you learn about, say, motion planning, it becomes much easier to learn about other algorithms, such as for perception, all things. If you learn about the basics of machine learning, it becomes really easy to get to understand more advanced machine learning and other concepts. So it might be a little hard to begin with, but stick to it and take things one at a time. And after you start your journey, it becomes easier down the line, and it becomes really enjoyable also when you can actually employ the skills that you've learned on real projects on creating real robots. So I hope that helped in giving you an overview of automation in general, where the field is at currently and what you can expect and the cool things that are there that you can try out and the cool things that are being done in research. So all the videos that I showed you were actually from research papers that have been released in the last few years. And actually, one of the videos on path planning, where the drone was navigating a cave, was done by one of ERC seniors. The research was done by one of the ERC seniors called Mihir Dharmadhikari at University of Nevada, Reno. So I think even Mihir might have been at the same stage you guys are at now, but in 4 years he managed to learn enough to be able to do that sort of research. So there's hope for all of us, and there's no need to get worried. And please check out the resources that we've collected for you. So that ends my presentation, and I'm sorry if I've gone a little bit over time. Oh, yeah, I've gone 1 minute over time without taking into account questions. So yeah, any questions? So what is the best place to learn C++? C++, we've posted a link on the roadmap. Yeah, the link is here. Yeah, there's a link to the a YouTube channel called the Cherno, I found personally really useful. It takes you from like the basics of C++ all the way to more advanced concepts, and you can learn it through a self-paced manner. And there are some examples also. So the Cherno's C++ C playlist is really good. You can also look at a few more. Yeah, you can also. There are also a few more resources posted in that section, so you can check those out also. Java, yeah, a few people have asked about Java. So, I mean, if you know that Java, that's great. It's probably going to be really easy for you to learn other languages. And if you're thinking about learning Java, I would recommend against it if you're interested more in robotics, since I think Java might be used in some places, but Python and C++ are much, much more common. So the robot operating system that we talked about, that has versions in Python and C++. Arduino is generally written in C. Also, any modeling or scientific computation that you might want to do is generally written in Python. So I would recommend picking either Python or C++ over Java if you're thinking about a language to learn. And if you know Java, that's great. It's really useful in other places, but for robotics, you might want to try out Python or C++. Okay, other questions? What is ROS? Okay, I think, yeah, I think I kind of gave a short note in ROS. I've provided a few links which really explain the whole concept and the motivation behind ROS in the roadmap. So check those out if you want to know. And if the question was about programming languages for ROS, yeah, like I mentioned, Python and C++ are used for ROS. Python is used for like simple sandboxing because it's a little slow, and on real robots and especially in research and more advanced applications, C++ is used. The C++ version of ROS is used. Okay, so our question we have is, what is the role of first years in ERC? Do we get to work on any projects, or we spend most of our time gaining skill required? So generally, if we were on campus, most of us got started learning different things while we were while we were working on projects themselves. And it's kind of both, right? If you you're generally allotted a task that you have to do for the project, and you have to learn some skills. So you spend some time learning about it, and then you solve the task. So it kind of works in tandem, working on a project and learning. And first years, but generally most of the time will be spent in learning stuff and uh, yeah, learning stuff about robotics. The kind of thing we're planning for you this year, as it's online, we kind of wanted to include a lot more people, which might not have been possible while we were on campus. But since we're online, we want to include a lot more people, and we're thinking of running mini projects. So you get the same kind of experience of working on projects, but they're uh, they're they aren't as advanced as they are usually, but they let you learn skills and apply those skills in a much in like much faster. And we're planning that these will run for a month or two, and we're planning to announce them this coming weekend. And yeah, they'll be started at least at the latest by next week. So you'll be able to work on projects definitely. There will be small beginner friendly projects, so you can learn skills and work on those projects. And yeah, the whole point of learning skills is to actually use them somewhere, right? So we hope that the projects will kind of be some motivations to start learning new stuff and exploring. Question is, automation and electronics is my thing, but is it necessary to have in-depth knowledge in mechanical design as well? So you don't, I mean, I personally don't have in-depth knowledge about mechanical and design, but there are other parts of members in the ERC who might be really skilled in one area, but might not know so much about the other. So it's not necessary to have in-depth knowledge, but then there are some people who are pretty knowledgeable about all three things, and they can accomplish a lot more than I can on my own. So yeah, it's great if you can learn all three things, but if you're interested in automation, definitely it's okay if you don't go in depth into mechanical. Uh, but one thing that is highly like recommended and kind of required also is that you understand the kinds of things that are there. So you understand what CAD modeling is. You can like kind of use maybe a program if you had to use it, and you understand like Dixit talked about the kinds of actuators that are there, the kinds of wheels that are there, all of these kinds of things. So you have to at least know the basic knowledge, because otherwise it becomes really hard to work in a team when you don't know the kinds of things that might be required for a robot. But after you have the basics, sure, you're free to specialize as much as you want in one field. So Dhruv Poddar has asked, what's the role of first years in ERC? Okay, I think I already answered this. So Chetan RS has asked, okay, yeah, I think that's all the questions that my team has relayed to me. If there are any more, you guys, I think, let's see. Yeah, there is a lot of questions about inductions in general. So I just like to make this clear that the ERC isn't inducting explicitly like some other clouds might be doing right now. But we have, as I said, some mini projects lined up starting from next week, in which if you want to get inducted to the ERC, you are expected to participate and contribute actively. And those people who contribute actively and show interest in those projects, and we'll also be having, yeah, so that show interest in those projects, they will be inducted eventually into the ERC. So we're hoping that this kind of thing will happen over the next semester. And you might feel intimidated in the sense that, okay, where do I start? And learning on your own is hard. So we've decided to keep a lot of intro sessions which are more in depth than these. So a lot of people want to know about Fusion 360 and CAD modeling. So we will be having a CAD modeling session in the next few weeks where you can, one of the ERC members will demonstrate how to use Fusion 360, maybe how to install it, use it to model certain items, and then give you basically enough skill to work on a simple project. And we won't just be having this for CAD modeling, but also for simple things like Python programming, maybe even robotics operating system. We'll be having it for how to use an Arduino. All of these basic skills that are required to work on a project. We'll be having intro sessions which you can attend. They'll be open to everyone, and you can attend, ask doubts, and you can follow along. And hopefully, they'll teach you the skills that are required to work in projects. So that's our plan for and after you learn this, you can contribute to projects, and those who show interest will be inducted. So that's our general plan for inducting people. I hope that kind of makes those induction related doubts clear. All right. We will be, those of you who are interested in electronics, we will be having a session soon about that also. So stay tuned, keep in touch on WhatsApp and on Discord. Another thing I kind of wanted to address was some people have approached us about projects they have in mind. Um, yeah, so if you have a project in mind and you kind of want to get start working on it with the help of ERC members, the best thing to do is to make a proposal, like write it down on paper, make a proposal of what the project entails, what kind of will be required, maybe even what components will be required, what expertise, how we will do, and try to go into as much detail. uh, Two things happen because of this. One, you understand your project more and you kind of go through the initial problem solving process on your own, kind of learn about some things on your own. And two, it becomes much easier for us to guide you then, and we don't have to advise you in some basic things that you should have discovered on your own. And it becomes that document can be a good place for us to begin working on a project if it's feasible. So yeah, that was that. And that's about it from my side for today. Thank you all for attending. I hope you learned a lot from the session. And if it's, I think the most asked question that I kind of wanted to address was where do I begin? And that's go to the roadmap. I've displayed the roadmap link, which is here. And I think it's there also, like we'll be posting it on the WhatsApp group also. So check out the roadmap. It has links in where you can get started, and after you start learning these basic skills, you'll be able to start contributing to robotics projects. So yeah, stay tuned for those mini projects that are coming that will help you get some hands-on experience. And that's it from the ERC for today. Thank you for attending, and yeah, I guess you guys are free now, and see you.